HighBridge, a division of Recorded Books, presents A Brief History of Timekeeping, the Science of Marking Time from Stonehenge to Atomic Clocks, by Chad Orzel, read by Mike Lenz. Publisher's note: in this audio edition you will hear references to visual elements present in the print and ebook formats of the book. Introduction. A clock is a thing that ticks. The picturesque campus of Union College in Schenectady, New York, where I teach, features lush, green quads surrounded by columned buildings full of classrooms, labs, and offices. Like most college campuses, it's also full of clocks. There's the tower clock in Memorial Chapel, whose chimes regularly ring out to mark the hours, and showcase the talents of the student musicians, who occasionally take over to play tunes on the chimes. A large decorative clock, a gift of the class of 1997, stands in front of the Reamer Campus Center, where it serves as a landmark for meeting people. Almost every classroom sports an analog clock on the wall for students and faculty to track the progress of class hours. Too fast for the faculty, too slow for the students. And, of course, there are innumerable unseen clocks, embedded in every computer, worn as wristwatches, carried in smartphones. Even beyond the physical presence of clocks, the tracking of time is ubiquitous on campus. Classes are scheduled down to the minute, start at 9:15 a.m., end at 10:20 a.m., start again at 10:30 a.m. in a different room, and meetings and appointments fill the day. Student work is often timed, 10 minutes allotted for an in-class presentation, an hour to complete an exam, and athletic feats are recorded down to fractions of a second. On a slower scale, the academic year progresses through a stately cycle of marked dates: the opening convocation, the start and end of the academic term, the annual Steinmetz Symposium celebrating student research. Every day brings students and faculty closer to the commencement ceremony that ends the year and sends a new class of graduates off into the world. All of this tracking and measuring of time is generally regarded as too routine to be commented upon. What's too often overlooked in the process of keeping on schedule and fretting about being overscheduled is the depth of history and rich variety of science underlying all this activity. We tend to think of our preoccupation with time as a modern phenomenon, but in fact, the tracking of time has been a major concern in essentially every era and location that we find evidence of human activity. Every historical society we know of had its own ways of tracking the passage of time, some of them dizzyingly complicated. Some of the most ancient architectural monuments we know of are calendar markers. A Brief History of Timekeeping is a virtual journey through the science that grew up alongside centuries of human efforts to measure the passage of time. Starting with the oldest known solstice marking monuments, we will explore the astronomy of the solar system and the features that determine the sun's path across the sky. Efforts to better understand the motion of the sun and planets led to the development of Newtonian physics, and we'll see how this enables the technology to build mechanical clocks. And we'll discuss revolutionary developments in the physics of electromagnetism and quantum mechanics that eventually led to the replacement of standards of timekeeping based on the motion of physical objects, like the pendulum of a mechanical clock, by modern atomic clocks that count the oscillations of light. The history of timekeeping is not only a story of abstract science and technology. It also includes intriguing elements of politics and philosophy. We'll look at the social aspects of calendar systems, like the intricate mix of cycles in the Mayan calendar at their peak around 500 CE, the theological considerations that led Europe to adopt the Gregorian calendar nearly 1,000 years later, and the political negotiations that produced our modern system of time zones. And we'll see how practical issues involved in these processes raised philosophical questions that, in turn, reshaped our understanding of our place in the universe as well as the nature of space and time. The tracking of time is, in a deep way, a signature preoccupation, not just of modern society, but of human civilization in general. The process of building and refining timekeeping devices has been one of the great drivers of progress in science and technology for millennia. From Neolithic solstice markers through mechanical watches to ultra-precise laser frequency standards, we are, and always have been, a species that builds clocks. Of course, a statement that sweeping depends on a particular definition of terms. In this case, we need a definition of clock that encompasses all these devices over a span of several thousand years. So, what is the common feature shared by solstice markers, mechanical watches, and laser spectroscopy? At the most basic level, a clock is a thing that ticks. The tick, here, can be the audible physical tick we associate with a mechanical clock, like the one in Union's Memorial Chapel, caused by collisions between gear teeth as a heavy pendulum swings back and forth. It can also be a more subtle physical effect, like the alternating voltage that provides the time signal for the electronic wall clocks in our classrooms. It can be exceedingly fast, like the 9 billion times a second oscillations of the microwaves used in the atomic clocks that provide the time signals transmitted to smartphones via the internet. Or ponderously slow, like the changing position of the rising sun on the horizon. In every one of these clocks, though, there is a tick, a regular, repeated action that can be counted to mark the passage of time. When the microwave field in an atomic clock completes an oscillation from up to down and back, we know that 1,9,192,631,770th of a second has passed. When the shadow cast by a building on campus sweeps across the quad and then returns to pointing due north, we know that 1 full day has passed. When the rising sun completes its seasonal cycle and returns to its northernmost position on the horizon, we know that 1 full year has passed. Each of these events is a metaphorical tick, and we quantify the passage of time by counting the number of these ticks that happen between two events of interest. It follows that one of the core themes in the history of timekeeping is the process of identifying and understanding these ticks. To make a high-quality clock, we must first identify a process that might serve as a tick, and then understand all the factors that change its rate and how those factors affect the ultimate accuracy of that clock. The drive to understand the process by which various kinds of clocks tick has led to revolutionary discoveries in fundamental science, particularly in physics and astrophysics, as we'll see in chapters 6 and 8. In order to time events by counting ticks, a practical clock must also have some sort of readout, a means by which humans can keep track of the count. While the audible ticks of a mechanical clock can, in principle, be counted directly, many of the physical systems used as clocks work at speeds that are impractical for human observers. The quartz crystal in my wristwatch oscillates much too rapidly to be counted directly, so its motion must be recorded electronically and slowed down to move the second hand 1 mark for every 32,768 vibrations. Many of the signature features we associate with practical clocks are these readout devices, the hands and numbers on a watch, or the gnomon and markings of a sundial tracking the slow motion of a shadow through the day. The history of timekeeping is thus also a history of innovation in readout technologies, finding clever ways to display the passage of time in human-readable ways that minimize sources of error. One of the most dramatic examples is the competition between methods for finding longitude at sea, described in chapters 9 and 10, a contest decided in part on the ability of ordinary sailors to use them. Another problem plaguing the makers of clocks through the centuries is that many excellent standards are impractical to transport. A solstice marker is fundamentally bound to a particular point in space, recording the position of the sun as seen from a particular location. If you shift the marker to another position, its references no longer apply. At the opposite technological extreme, a precision atomic clock requires a significant infrastructure for the preparation and interrogation of atoms, keeping the very best atomic clocks confined to laboratories. Many of the practical clocks we surround ourselves with are thus actually models of clocks, a way of keeping track of time that approximates the time recorded by a better standard tick that is inconveniently immobile. The clock on the wall of my classroom displays only an approximate time based on the oscillation of the electric current supplied from the power grid. The official time is determined by an assortment of atomic clocks in national standards laboratories scattered around the globe and overseen by an international governing body. We'll discuss the origin of global time zones and the determination of the official time in Chapter 11. Because most practical clocks are models of time, a third core theme in the history of timekeeping is the idea of comparing clocks to one another, and using that comparison to refine our models of time. The fundamental process is universal, employed by every civilization that has modeled time. You synchronize your model clock with some standard, allow it to run freely for many ticks, then check it against the standard again, and see if they're still in sync. It's the same process you might use to check the performance of your watch. You set it to the correct official time, say, using the U.S. time webpage provided by the National Institute of Standards and Technology, NIST. Wear it around for a while, and then, some days or weeks later, check it against the official time again, and adjust as needed. Even though the quartz crystal in your watch is not connected in any direct way to the cesium atoms in atomic clocks at NIST, this process ensures that you carry with you a very good model of the actual official time. Through the long history of timekeeping, this process has been used to produce dramatic results on a variety of timescales. As we'll see in Chapter 12, the process of synchronizing two clocks at different locations through the exchange of telegraphic signals was central to the development of the theory of relativity, with momentous consequences for our understanding of time and space. At the other extreme of duration, as we'll see in Chapter 3, the Gregorian calendar reform grew out of this synchronized, free-run, check process applied over the course of centuries. The Gregorian calendar is also an important illustration of a fourth theme: the way the sheer depth of the history of timekeeping enables incredible precision, even with crude tools. Thanks to calendar records spanning thousands of years, from Roman times through the medieval period and into the Renaissance, astronomers could detect a difference between their model of time and the cycle of seasons that amounts to just 11 minutes per year. Following the synchronized phase of calendar reform in 8 CE, the Julian calendar ran freely for more than 1,500 years before its final check, which led to the introduction of our modern calendar by Pope Gregory XIII in 1582. The Gregorian calendar will stay in sync with the seasons for another 3,000 years, despite being implemented 2 decades before the invention of the telescope. You don't need atomic clocks with nanosecond precision to make highly accurate measurements of time, provided you can wait long enough. Pulling all these elements together, we can see the history of timekeeping as a progression through a long series of standard ticks and tools to model them. As our knowledge of science has advanced, we have found new ways to measure more subtle effects, allowing a move to better standards through a kind of bootstrapping process. A new candidate tick is first verified against the best version of the current standard. And then, as the processes behind the new standard become better understood, it eventually surpasses the precision of the current standard and then supplants it. This is nicely encapsulated in the changes in the official definition of time through the 20th century. When what became the modern International System of Units, SI, was introduced in the 1870s. 1 second was defined as 1/86,400th of a solar day. This was an adequate definition for clocks at that time, but the rotation rate of the Earth changes over time. A solar day in 2019 is nearly 2 milliseconds longer than a day in 1870. As state-of-the-art pendulum clocks and quartz crystal oscillators were developed in the early 1900s, their precision advanced to the point where the intrinsic uncertainty of these model clocks was smaller than the ambiguity introduced by the definition of a day. Removing this ambiguity required a change in the definition of time. In 1960, the definition of a second was officially changed to the fraction 1 over 31,556,925.9747 of the tropical year for 1900 January 0 at 12 hours ephemeris time, tying the second to the well-understood motion of the Earth about the Sun. Of course, it's impossible to keep a copy of the tropical year 1900 around for reference, so physicists looked for a more convenient and universal standard. They eventually found one, thanks to the quantum nature of atoms and light. The frequencies of light absorbed and emitted by atoms are uniquely determined by the laws of quantum physics, and every atom of a given element is identical to every other, making atoms a convenient and somewhat portable, more so than the year 1900 at least, standard for timekeeping. With the completion of quantum theory and the development of high-precision microwave spectroscopy, which we will discuss in Chapter 13, it became possible to decouple the definition of time from the slowly changing motion of the Earth. In 1967, the definition of the second was changed to the duration of 9,192,631,770 periods of the radiation corresponding to the transition between the two hyperfine levels of the ground state of the cesium-133 atom. This has remained the official definition, the tick that we count to track what time it is, and the best atomic clocks today would need to run continuously for 1 billion years or more before they would gain or lose a single second. The cesium standard is not necessarily the final definition, though, as physicists and engineers have continued to experiment with newer and better types of clocks. There are experimental clocks under development in standards laboratories tens or hundreds of times more accurate than the best possible cesium standards. A clear favorite has yet to emerge, but not too many years in the future, we may see yet another redefinition of time, moving away from cesium to an entirely different element. We'll discuss these next-generation atomic clocks in Chapter 16. There's one final essential theme that runs through the history of timekeeping. Tracking time is not just about the past, or even what time it is right now. The science and technology of timekeeping are also bound up with projecting time forward. Timekeeping helps impose order and predictability onto an otherwise capricious and confusing universe. A reliable tick that we can count to determine how much time has passed is also a process that will continue happening on into the future, giving us confidence that we can understand and predict what will happen. This forecasting element shows up throughout the history of timekeeping all around the world. We see the evidence of Neolithic cultures setting up monuments to mark the winter solstice and provide a reminder of the spring to come. Jews and early Christians adjusted their calendar systems in order to predict the dates of Passover and Easter years into the future. Mayan astronomers tracked the motion of Venus to predict auspicious times for war. European mathematicians developed elaborate models of where the moon will be to help sailors navigate their way through globe-spanning empires. There's even an element of this forward projection in modern efforts to push the frontiers of atomic clocks. We don't need that level of precision right now, but it could provide the key to exotic discoveries in the future. Through all this history, from ancient agrarian societies looking for the best time to plant crops, to astrologers trying to read the future in the stars, to astronomers predicting transits of celestial objects, timekeeping has always been as much about the future as the past. That predictive element shows up again and again, from the most ancient builders of stone monuments all the way to modern office workers entering future vacations into digital calendar apps. In modern society, we expend an enormous amount of effort on the tracking of time, supported by a vast and largely overlooked foundation of science and technology. The development of that foundation is a story that spans several thousand years and incorporates an enormous amount of scientific knowledge. That's a history that's worth taking a little time to explore. Chapter 1. Sunrise. In the late 1600s, the Glorious Revolution deposed the Catholic King of England and Scotland, James Stuart, replacing him with his daughter, Mary, and her husband, William of Orange. This triggered a number of uprisings in the British Isles, including the Williamite War in Ireland. After the uprisings were put down, large tracts of land were confiscated from James's Catholic supporters and redistributed among William's Protestant backers. One of these parcels, an estate near the port town of Drogheda, passed to a man named Charles Campbell, who set about making improvements to his new property. To this end, in 1699, he ordered a crew of laborers to begin quarrying stones from an overgrown rocky mound on a hilltop. This mound was one of many dotting the landscape in the area known as the Brú na Bóinne, Palace of the Boyne, which was strongly associated with the gods and heroes of Ireland's pagan past. Not far into their quarrying work, Campbell's crew uncovered a broad, flat stone, rudely carved and placed edgewise at the bottom of the mound, blocking the entrance to an artificial passage fashioned from enormous stones standing on end. This discovery brought the quarrying to a halt and attracted the attention of Edward Lloyd, the keeper of the Ashmolean Museum at Oxford, who happened to be traveling through the area. Lloyd described his visit to the cave in a letter to the Royal Society, which is the first published description of the passage tomb now known as Newgrange, and the source of the quoted description earlier. Over the next couple of centuries, antiquarians and treasure hunters made occasional visits to Newgrange in the haphazard manner of the times, thoroughly muddling the archaeological record and producing several confused and mildly contradictory accounts of the tomb and its contents. The large-scale structure of the mound was largely undisturbed, though, until a massive excavation was undertaken in the 1960s by Irish archaeologist Professor Michael O'Kelly, who carefully removed the tons of earth and rock covering the passage and central vault, and in the process made a remarkable discovery about the purpose of the structure. While excavating the entrance, O'Kelly discovered the roof box, two parallel slabs of rock placed horizontally just above the entrance to the passage. The gap between these slabs was closed by blocks of white quartz. Marks on the stones suggested these had been removed and replaced repeatedly. A local tradition related to the O'Kelly team during the excavation held that, at some unspecified time, the rising sun used to light up a carved stone at the very back of the tomb. On the basis of this legend, and the site orientation surveys done during the course of the excavation, members of the team entered the central chamber in the pre-dawn hours of December 21st, 1969, and recorded a remarkable phenomenon. At exactly 8.54 hours GMT, the top edge of the ball of the sun appeared above the local horizon, and at 8.58 hours, the first pencil of direct sunlight shone through the roof box and along the passage to reach across the tomb chamber floor as far as the front edge of the basin stone in the end recess. As the thin line of light widened to a 17-centimeter band and swung across the chamber floor, the tomb was dramatically illuminated, and various details of the side and end recesses could be clearly seen in the light reflected from the floor. At 9.09 hours, the 17-centimeter band of light began to narrow again, and at exactly 9.15 hours, the direct beam was cut off from the tomb. For 17 minutes, therefore, at sunrise, on the shortest day of the year, direct sunlight can enter Newgrange, not through the doorway, but through the specially contrived slit that lies under the roof box at the outer end of the passage roof. To everything there is a season. Turn, turn, turn. We don't necessarily think about a solstice marker like Newgrange as a clock, because of its monumental scale and the fact that the associated tick is so slow, occurring just once per year. This is not a device that will help you determine how much longer you have to endure a tedious lecture or wait for the arrival of a dinner companion. It unquestionably fits the broad definition spelled out in the introduction, though. The appearance of sunlight in the central chamber provides a clear readout for a physical cycle that repeats at regular intervals and can be counted to track the passage of time. The physical process that provides the tick for a solstice marker like Newgrange is the motion of the sun through the seasons of the year. For people who live in the middle latitudes, like the builders of Newgrange, or residents of the northeastern United States like myself, the year is a march through winter, spring, summer, and fall, returning to winter again. These changing seasons are associated with changes in the length of the day. In the winter, the sun rises late and sets early, while in the summer, it does the opposite. As the caregiver for an active dog who needs multiple daily walks, I'm acutely aware of this. During the winter months, from November through March, both our post-breakfast and post-dinner walks take place in darkness. During the short days of winter, the sun shines for less of the day and thus has less time to heat the surface of the earth, leading to colder daily temperatures. In the summer, longer days mean more heating and higher daily temperatures. There's a bit of a time lag in the cycle. The hottest days of summer are generally a few weeks after the longest day of the year, and the coldest and snowiest days of winter come after the shortest day has passed. This happens because the Earth is huge, and it takes some time for heat to accumulate or dissipate. The seasonal cycle of weather is accompanied by seasonal changes in plants and animals. As the days get longer and the weather warmer, plants begin to grow and animals become more active, while as the days get shorter and the weather colder, trees lose their leaves and animals hunker down for the winter. These seasonal cycles are of critical importance to human civilization even today, with global transportation networks ensuring access to fresh food year-round. They would have been a matter of life and death for the agrarian Neolithic society that built Newgrange. This very obvious seasonal change in the length of the day is accompanied by a somewhat less obvious change in the positions of sunrise and sunset. While we learn as children that the sun rises in the east and sets in the west, this is strictly true for only 2 days of the year. Only on the equinoxes, in late March and late September, does the sun rise due east and set due west. The March equinox is often called the vernal equinox, and the September one the autumnal equinox, reflecting the seasons in which they occur in Europe. I'll stick with the month names here, though, out of respect for the feelings of those in the southern hemisphere. During the short days of winter, the sun rises south of east and sets south of west, while the long days of summer see the sun rise north of east and set north of west. In the mid-latitudes of the northern hemisphere anyway, where both Newgrange and my home are located, In the mid-latitudes of the southern hemisphere, the
Sample complete. Ready to continue?